something. Okay, what I got for today? Right? What foremost? What I'm got for today is an overhead line parameters. In a good theory, each line of the commission came with a nice set of documentation with nice papers, where all towers are all towers geometry is invented, all towers are in geoinformation system, all distance are known, everything fine. In reality, project company is just an office, construction performed by a bunch of subcontractors. At some point, towers are replaced with cheaper models, different wires are used, and so on and so on. Instead of high-class surveyors, and so on and so on. So, what I'm talking about, you have a power line, you're able to measure geometry, but what will be line constant? What will be electrical values? You are preparing to become a leading engineer. So leading engineer should be, in theory, should be able to determine line parameters from its geometry. At line, have an idea what it is possible. Let's say one tower, second tower, we have a protective cable, light protecting. I will use Latvian truss. I will use P. Insulators, 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 insulators. One phase wire, two phase wire, three phase wire. Here, let's say it's powered from this will be A, B, C, and somewhere here we have a huge earth fault. Maybe yeah, huge earth fault. So we have A phase current, C phase current, B phase current, but that's not all. We have ground current. Z from Latvian zeme. It's a ground current. Also, from the current will to the nearest to the fault place tower, current will inflow into the protective cable. So it's a current and protect in your lighting protection. problem is complex because first you need to account, let's say, okay, wire to wire inductance, but that's not all. You need to account mutual coupling between wire and the ground current, and that's not all. You also need to tackle coupling between wire and lighting protection. Whole set of mutual inductance. You need to account all of this to get real values, electrical values for your model. So you will see three inductance via wire, three inductance via protective cable, three inductance, mutual inductance via ground current, and inductance protective cable ground. Also, maybe in green. This also is here. Quite a complex task, isn't it? At first, we can start, let's say, from the core task. Actually, it's in two tasks. So you have conductive ground, wire over conductive ground, let's say powered and somehow loaded. You have wire over conductive ground, and second wire. You need to establish or estimate parameters, ohm or self-inductance. For this one, you need at first self-inductance and self-resistance. It's number one. And second one, it's a meter. You should be able to estimate coupling between two wires over conductive ground. If you can solve these two tasks, you can solve task of line parameters estimation. Historically, there are two approaches to this problem. One is Carlson's model, and second one is Rydberg's. Carlson model starts with idea you have flat conductive ground and wire over it. 1926, with the height of h. So in Carson's model, Earth is flat. Rydberg's model believes what y is in a kind of semi-pi. This is Rydberg's idea of Rydberg's model. In some German-speaking countries, Rydberg's model used till this time, but actually, in my view, Rydberg's model is not practical, because Rydberg was against model transformation. Rydberg model is not suitable for symmetrical components. Actually, it can be used, but in general, Rydberg was against symmetrical components. And I like symmetrical components, they simplify life. So Carson model acts, let's say, in concordance with theory of symmetrical components. Actually, Carson published his work, it called Wave Propagation in Overhead Lines. It's 1926. Carson based his model on nature measurements, future amount, it's Lewis work. What's interesting in nature, in real measurements? First thing, the guys try to build a line and measure real. First thing, if your line makes a loop, it can be expected what current and ground will flow through the shortest path. No. In reality, ground current follows the line. So if line makes a loop, ground current follows. Ground current follows line, not goes to the shortest path. It's one thing. Second, if this is y, measuring of current density on a surface showed something like this. If x is a distance from y, Hertz, 60 Hertz, bit lower, but level of 1/4, this point is approximately 2,000 feet. What Carson assumed? See, I saw this somewhere. Also measurement, if in depth measurement, if depth also, picture like this from the wire. What Carson assumed? I saw similar current distribution. Carson assumed, let's say proposed, interesting approach. Carson proposed to substitute model wire over conductive ground with two-wire model. Second, or imaginable return wire being, this is called return depth, assuming that all current flow in this imaginary return wire. This distance is approximately 1,000 meters. Carson's idea was to use two-wire model with same current density distribution. Why? Because Carson knew solution for two-wire system. Idea was to find two-wire system with a similar current density distribution, and for this system Carson knew already solution of own and neutral parameters. This equivalent current return is deep in the ground, and this value is known as equivalent current return depth. So if you put a superconductive wire in the depth, you will see the same current or field distribution. Really, density of current at this depth is only 5% of current will be observed here, approximately. This equivalent depth is a function of two parameters. One is a ground conductivity, and second, frequency. It depends on frequency. Carson's solution wait, should be 658,368 square root Earth resistance frequency. Rho, Earth resistance, measurable in ohms per square meter. So if you will take, let's say, plastic pipe with a cross section of 1 square meter, fill it with this ground, and length should be 1 meter, you will get lowest for seawater. For seawater, you will have approximately 1 in 100, 1 in 10. Baltics is less salty, so resistance will be high. For swamps, it's approximately 100. Water-rich ground, like here we have water-rich ground and horrible lands, it's approximately 100. dry soil, 1000 pure pure slate, something like 10 with the 7 zeros, and dry limestone. Here, in Latvia, real things on the set are approximately 9 30 meters. It's real, but very often average value of 1 kilometer is used. Real calculation is it's shaking. So, line on resistance. What's that? Oh. Так, so on via resistance maybe, okay, line resistance will be omega L logarithm divided by Rg. What is Rg? It's a geometrical mean via radius. Idea what real wire can be substituted with pipe with infinity thin wall and radius of this pipe will be Rg. It's a geometrical equivalent. Pipe with very thin walls have superconductive pipe, superconductive pipe with a very thin wall being equivalent of the real wire cross-section. When the trick is, see, magnetic field will be around wire, but also in the wire, inside. To take into account that in reality we have two fields in two different mediums, this equivalent is used. Where is my block? So this idea, what wire inductance contains of two parts, internal and external. Internal is, let's say, connected or concerns magnetic field inside the wire, in the wire. Wire is not infinity thin. Wire has size. So there will be magnetic field in the wire and around the wire. And we can speak on two inductance. internal and external. At the beginning we have two wire line and distance. This distance is much bigger than the wire internal. Where is my wire? Wire radius. So distance between wire is much bigger than the wire radius. In such case, we can assume what there is no skin effect, and magnetic field inside its wire is uniform. If we have two very close wires, when distance between wires is less than the wire radius, this will see a different picture. So if we have, say, wire with magnetic conductivity MV in the area with isolated area, dielectric area with magnetic conductivity D from dielectric. So we have wire with magnetic conductivity in the area or image of the dielectric with magnetic conductivity mu D. It's a Crookes formula. Internal plus external, and it will be mu0 length divided by 4p and multiplied by 4 natural logarithm F0, it's an F0 divided by F0 plus divided by this medium conductivity. I use a Crookes formula. Since general distance between wire, we are talking about overhead lines, is much bigger than the wire radius, and magnetic conductivity of the air is 1, this can be a bit simplified. So inductance will be mu0 line length divided by 4p. Here will be 4 natural logarithms divided by F0 plus or 0 8p natural logarithm of d e power mu y divided by 4. 1 second. One second, and should, yeah, now it's correct. Zero. Yeah. Yeah, here it is. This way is correct. What's next? The value equivalent it's an equivalent being F0 divided by F power mu y divided by 4. Equivalent it's also maybe called geometric mean radius. It's an equivalent for your wire. It's an equivalent radius or geometric mean radius. For monolithic, for solid copper, this equivalent it's for 779 F0. It's for monolith copper. Aluminum big different. What's forward? At some point, let's say common opinion in industry was to switch from natural logarithm to decimal. And common form today more workable is length divided by 8p divided by L0 was logarithm of 10 power by 4. What is after simplification will be mu 0 length divided by 8p decimal logarithm of e decimal logarithm divided by R0. Instead of equivalent radius, often use so-called GMR. There is a difference, actually difference between equivalent and GMR. Equal GMF, geometrically mean radius, is L0 divided by 10 power mu y divided by 4. It's for monolithic. For multi-conductor wires, multi-strand wires, approximately for 7 strands, it will be 0.726 multiplied by R0. For 37, 0.768, and for large 127 strands, 0.776. The same. Actually, it's empirical data. For huge wires, real huge wires, observed erga or GMR is frequency dependent. There are well-known measurements for American standard 2 million circular mills. It's approximately 1,250 square millimeters. Erga at 25 Hz was observed 1.615 centimeters. At 50 Hz 1.643, and in 60 Hz 1.6612 centimeters. So 50, 60 Hz, some 1%, but at lower frequency, something more, let's say, bigger effect. If you need, it's a very good source for such data. American Bureau of Standards have a set of publication. They measure this data real, so it's a result of real measurements. Copper and aluminum wire tables are published by United States Bureau of Standards. Copper wires are something expensive. More popular are steel aluminum. Yeah? Steel core aluminum shell or aluminum body with steel reinforcement wires. For reinforcement in the outer shell is one story. For steel core, you will see something like two layers, 26 strands, 809 multiplied by F0, 3 layers, 54 strands, 081 and one layer, 6 strands. At low current 0819 with the current 7.5 amperes per square millimeter, 07087, and with doubling current 15 amperes per square millimeter, 0367. It's a problem because what's the source of this problem? Magnetic fields pushes current to the outer, let's say, outside of the wire. Real good date for your wire, good manufacturers publish tables for their wires. Good manufacturers. One more, usually one single wire is used for up to theory up to 500 square millimeters. For higher current densities, it's not practical to use single wire. And split wires are used. Starting from 2-wire system, split by 3, by 5, up. I saw a picture of 9 in one phase. Split system. In such case, Fg for whole system summary will be square root of n power, where n is a number of wires in split. GMF for one wire multiplied by GMF, distance between wires. Okay. Let's go forward. When it's more practical for us, obtain 1 kilometer resistance. 1 kilometer we can write as 0.14468 decimal logarithm by GMF. But that's not all. we also need active resistance. And its active resistance, it's very what? Because it's contained two parts. Ohm wire active resistance plus ground resistance. We have ground return. Real measurements 1950, 1921, 1922, it's Lewis work. Lewis built AT&T, founded this, built a lines and measured what? Voltage, current and power losses. Ground source on earth. Line, ground. And lens. Current for testing. What Lewis found? What this system, active resistance, in paradoxal way, is independent from the Earth resistance. Earth conductivity plays virtually no role in the system's equivalent resistance. Why? Because on the dry source with higher resistance, current flows, let's say, wider. It takes larger area. We have a good conductivity, wet soil or water, current flows in narrow, let's say, corridor behind the line, not behind, but under the line. Very approximate ground resistance can be found as P square frequency multiple length ohm. More detailed model was developed by Carson's, and Carson's model relies on a parameter being 1.713 and square root frequency Earth conductivity. H is a height via above ground, distance from ground, frequency and Earth conductivity. Active losses in ground for small betas. It's one moment. How many people do make a mistakes? This Carson had a quite precise formula, but for bets less than 1/4. For higher beta, this formula can be used. It's for normal line where tower is high enough. For some stupid special cases, low tower and so on, this is not applicable. Empiric Carson's formula is something like this. 2.51289 frequency 10 minus multiplied by 1 divided 3 square root of beta plus beta squared divided by 16 0.6728 plus natural logarithm of 2 divided by beta multiplied by length. For higher bets, Carson gave a table. There is an approximation curve. For more detailed, when needed, you can check on the name Dubantons. There are Dubantons extension to Carson model. This is nice, but that's not enough. We need to account magnetic coupling between wires. This is not enough. First solution is for zero sequence. Let's start with zero sequence. So we have star connected source. Let's say I have applied zero sequence source. I have 1, 2, 3 wires. It's A, B, C. They all come together and rest. Here I will observe triple zero sequence current. Here falls 0, 0 and 0, 0 sequence current. And I can add voltmeter. It will show me voltage drop in zero sequence. Delta is 0. Here, ground current, triple zero sequence current. This is model for zero sequence. I need to derive something like this. Zero sequence voltage, zero sequence current, zero sequence complex resistance. I need to derive this lamp model in terms of electrotechnics theory from 3 wires over ground Lewis did some work for me. Okay, it was for Carson. Lewis performed a measurement on such model. AC source, ampere, volts, wattmeter, grounded. A line and second line, they are coupled. Here I can put a meter. On such model, yeah, I need to show length. Here flows current A, what we will see in line B. On such test model, Lewis performed set of measurements. Based on them, Carson developed his model. And Carson's model is a complex thing. So, you have ground. Above ground, it's an A line. We have wire on the HA. Let's say current goes this way. Return wire is in ground. This distance is D. Yeah. So line A with its return here, line B with its return in the ground in equivalent depth, equivalent current return depth is the B. This distance AB and a key element is this angle. That is an angle between, let's say, A line axis and coupling axis. Let's say distance between them. Here is Carson's model. For such model, Carson got not a complete solution, but quite usable, empiric solution. In its solution, metal inductance resistance is 2.77493 and minus third. Frequency, decimal logarithm, AB divided by small AB. Yeah, and the small dab is equals to x. It's a distance. This one is AB small, and this will be capital. Plus, yeah, we're making a mistake. Why it's 1 second? I just was ready to make a mistake. X, if this is A, if this is B, X is a distance on the Earth's surface between vertical lines. AB is between wire and AB capital between A line and a B line return. I was near to make a mistake, writing what this is equal to X. It's true only if wire placed horizontal. So, what I'm willing to write? 2.51 2894 multiplied by 10 minus 3 multiplied by people's losses. P parameter B bet here will be 8.565 multiplied by 10 minus 4 DAB square root frequency divided by equivalent resistance. We need to account theta being arctangents of x divided HA plus HB values are for small bets. It's a limit. Bet should be less than 1/4. In such case, active loss will be P divided minus 1 beta cosines plus beta square divided by cosine 2 theta multiplied by 0.6728 natural logarithm divided by beta plus beta square divided by 16 theta sinus double theta. Not an easy formula, isn't it? And it's approximation, and it's for small bets. For larger, seek for Carson work, you will see a good chart of nature of real measurement. For reactive power, Q usually is calculated as 0.0386 minus natural of beta by nature by tau plus beta cosine theta divided by 3 square roots of 2. Usually, people think, oh yeah, the tower is tall enough. There is a moment, the LS of this angle theta. If you have normal situation, quite tall tower, and relative small distance between face, theta will be small. And usually, in your books, if you have some books, will be something like 88 minus 4 frequency plus your 2.8938 frequency multiplied by logarithm x50 0.368 square root divided by frequency and VAB. I can bit simplify. The 8 10 minus frequency plus your 2.8938 divided by 10 frequency logarithm divided by AB. For 50 Hertz, this value will be 494 plus your 0.14469 logarithm by DAB. This is for 50 Hertz. That's what you will see in most books. This formula is true for small betas. Bet should be under 1/4. This means it's for normal line. Actually, if you perform a high precision modeling, you should check real value of beta. If you have what can play low towers, real low towers, and larger distance. For normal, the height of tower is, let's say, determined by safety, by safe level of electromagnetic field for people walking under this line. It's the height of tower. Of course, also plays if there is traffic below the line, you need to obey height of average transport machine. If there is a river, you will get a limit height of the tallest ship. So ordinary towers are quite high, and height of tower is greater than the distance between one. But if you have something like 750 kilovolts line with separate tower, and they are wide. If you look on such a line, they are wide. If ordinary lines are tall, super high voltage lines are wide. Check the beta.
The high voltage cables are insulated or non-insulated? Super high voltage.
Super overhead, no, there is no reason to insulate them. Real insulated cables and somewhere around 24 kilovolts is a reasonable upper voltage. For higher voltage, it's not profitable. In reality, we have a wave of line conversion, 20 kilovolts line, to insulated SAX type of wire. Actually not PACE. They do not withstand light over voltage. They should be, in theory, they should be cheaper on maintenance costs because accidental contact with the tree branch do not cause fault, so it's cheaper. But in reality, reality shows what best way is simple to switch to underground cable. In the populated areas or in dense forest areas, it is more profitable to use underground cable because maintenance cost drops. It's our reality. Okay, from this one, ohm can be found. So, ohm or self will be L1 plus 4.94 multiplied minus 2 plus 0.14469 decimal logarithm divided by GML. It's taking into account ground current. Now more serious. We need to get some mass for free wire system. So I have A, B, C phase, width CA, DAB, and DBC, distance between them. All this is above of conductive earth. And to make our life simpler, let's assume what line has a full transposition circle, or for the whole line it's equal coupling with the ground current. It's an important moment. It's what's been done at let's say ground level, at the, starting this theory. If you need a high precision modeling, this trick will not work for you because in real high precision situation, when you need a high precision, you will not have a full transposition circle. And distance between wires and their ground returns are not uniform, are not equal. So this works if you have a full transposition cycle. If your line is symmetrical relative to ground. If your line is symmetrical, current will distribute evenly. I can work with the model like this. I have three wires, A, B, C. Yes. They are above conductive ground, yeah? I assume current source, not powering all of this. And 1/3 of the current flows in each line. Yeah? Here current will be triple. What I need? I need a voltage drop. Let's assume it's 1 kilometer. I need a voltage drop per kilometer. This will show me zero sequence resistance. What I need to deal with? Ampere source in L owned by resistance. It's a self, yeah? One, I will need two of them. This will go to ground. It's an A phase. For B phase, free source. Again, self. It's a self for B phase. And what's this? AB mutual inductance. It will be presented as mutual resistance, ZAB, complex. They are complex. And for C phase, again, sorry, it's for C phase. BC, or maybe I will use an index and one more. It's ZMAB or AC. Here I have return wire, here is ground, and here is returning as a ground current. Here is my model. So each wire has own or self-resistance and two couplings, two mutual. So I need to solve cell for A phase, mutual AB, mutual AC. Yep. By 3 by 3 ZSB M it's AB BC and third one C metal BC metal AC. Case schematic I need to solve. I need any of voltage drop. For example, this one. This voltage drop yields me a 1 kilometer resistance. What means transposed line? What idea? What means transposed line or transposition circle? To avoid line asymmetry, at first by capacitance. Trick is done. A, B, C. Next swap. A, B. For example. First transposition stage. What will be next? Next, B should go up. Something like this. And so on and so on. Yeah, nice picture. Yeah, transposition. Idea is to make capacitance via ground equal for whole line. So it's idea of transposition. For the first one, I will have for A phase 3 A plus Z mu AB plus Z mu CA. Yes? Delta will be B plus AB plus ZMBC, and for C phase it's again AC plus ZMBC plus metal CA. If we start with the full transposition circle. Each face takes all three positions, yeah? And if each face takes all three positions, for full transposition circle, for each face we need to sum this. I wrote this for one transposition point. For one, let's say, from point to point, from transposition one, barrel to barrel, transposition barrels. If we assume full transposition circle, full symmetry, I need to sum all this for each phase. Meaning what? For full transposition circle, I will get 3 A plus AB plus ZAC plus double MAB plus ZMBC plus ZCA. So for the whole line, delta U will be divided by 9, 3 line self-resistance plus double sum ZAB plus, MAB ZMBC plus ZMCA. Note, this is not for 1 but for 3 kilometers, for whole line. Now I can get zero sequence resistance for the 50 Hertz. Since I know both self and neutral inductance, or whole resistance, I knew also active component. So, for the whole line, I will have multiplied by plus 3 multiplied by 4.94 plus got 3 multiplied by 14469 logarithm Rg plus 6.494 plus my board is ending. So continuing plus yield 0.1469 multiplied by double logarithm is DAB plus logarithm is BC plus logarithm DCA. I hope I simplified it correctly. I hope I make no mistake. So it can be rewritten as by 9 multiplied by triple y plus 9 multiplied by 4, 94, 0.1469 multiplied by 3 decimal logarithm is divided by erga plus double logarithm of dz divided by ab plus logarithm bbc plus logarithm of dz divided by dca, sorry, two brackets. Blah, blah, blah. So, finally, for the 1 unit of line length, should be L by 3 plus 494 multiplied plus 0.1469 multiplied by decimal logarithm of divided by square root, not square but root of power 9 of erga VAB BBC DCA, and this should be square. Zero sequence resistance of one phase per unit being 3 delta divided by will be wire resistance plus 1482 plus 43 divided by root of power 9 and got u DAB DBC DCA square ohm per kilometer. Nice formula. That's what you will see in your handbook. But this formula is true for small betas and for fully transposed lines. This formula assumes line symmetry. It's okay for faults, but when we speak high precision fault location, this formula not work. For simplification, average distance is used. It's a square root of DAB DBC DCA. And average geometric radius for whole line. For whole line, sigma, sometimes it's also marked as a GMF, but this is GMF for whole line. It's a root of power 9 from G cube average distance in power 5, so can be written as a root of power 3 from Fg dv square. Finally, Fy plus 0.1482 plus 0.307 multiplied by logarithm by this whole line. This is GMF for whole line. Yeah. Nice. Can we go further? We will die here. Yeah.
Capacitance on transmission line. Capacitance of three-phase line with equivalent phasing.
You need a capacitance coefficients.
Coefficients, okay.
Yeah, it's potential coefficients.
Okay.
It's where is my nice book?
Yeah. But it's a lot.
You can. It's available online. You can fill it to online translator. Capacitance is not so important for us, but it's there. Maybe. My short trick, how I can get a direct sequence resistance. This formula is for zero sequence resistance. If you need online version,
Yes, you have.
yeah, we have online version. Can you go into Dolgitsa's point F point? Okay, I knew address directly. Yeah, now here.
It's a PDF.
Yes, it's a PDF.
I can translate it.
Yeah, it's something familiar, isn't it?
Yeah.
Sequence, go forward.
Which page number? How do you calculate focus radius?
appendices are calculus examples. Start. Yeah, here it starts. 2.2. It's on the its capacity. And there are numeric examples in appendix. Not I did it either. What I want. Put it in. Okay, what I want. From this short go forward, I need a direct sequence parameters. Zero sequence I obtain quite easily. How can I get a direct sequence? Idea, I can use the same model, but setting A phase current as a square and as an it's correct. When? Why? Because sum of current will be zero, and I can ignore wire to returning current inductance. I can ignore return wires. So for the first transposition stage, let's say I will have 1 as ZLA plus A square ZMAB plus A ZMCA. On the second transposition stage, I will have Y3 LB plus multiple AB multiplied by A plus multiple BC multiplied by A squared. And for the third, stage, I will have A3 ZLC plus A squared AC plus A BC. Yeah, that's what I get. I need to sum them. It's for first, second, and third stage of transposition. Summary voltage drop will be sum of them. So I will get something like this. Common voltage drop will be 1/3 of my current, ZLA plus ZLB plus ZLC plus A plus RA squared multiplied by multiple AB plus multiple BC plus multiple CA. That's what I will get. Was 1/2 minus your square root. This one is equal. So it will be, sorry, 1/2. It will be -1. You understand why? This one equals to -1. So I can write just putting minus here. So what can I write? I can write I will use values for self and mutual resistance. Equals to multiplied by L bar plus your 0.14469 decimal logarithm divided by mean geometric radius minus your 0.14469 logarithm of divided by root of pi 3 of B, A, B, 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 C, B, C, A. Interesting. Interesting thing. What mutual here, mutual inductance not increases line resistance, but decreases. I got minus. Can revise. Delta will be current by wire resistance plus 0.14469 logarithm B A B B B C B C A divided by. So direct sequence resistance contains of wire resistance on plus 0.14469 dV divided by mean geometric radius. Difference here. It's a difference between direct and zero sequence. Uh, 0.14469. dV. It's a difference value. If you like, you can write zero sequence as a kind of line resistance plus double mutual, direct sequence again equals to negative sequence and equals to some average rate line minus delta. For usual line, these values are close. Are close, but difference between direct and zero sequence is quite significant. It's approximately 3 times. I can point to one thing, what line resistance being double direct sequence resistance plus y, simple zero sequence resistance by 3, and this difference in minus direct sequence resistance divided by 3. When we will speak on distance protection, you'll see this element. And what should I know? Huge. You'll see similar formulas in many different books. They are traveling from one to another without noting what these are for line with full transposition cycle. very few out really understand what they should understand. What if we need real high precision and we don't have full transposition, we cannot use this model. We need to return to phase coordinates and perform a calculus based on real Carson model, taking into account all elements. But if you need real high precision, there is Carson model. But Carson model, Carson model with Dubanton's extensions, it's more precise. Wedge-Paul model is more precise than extended Carson. But if you need real high precision, go for the Hofmann's model. It's 83 or 84, 1983. Hofmann's model, but be prepared. Okay. What left? What left? What? Protective wire. I think it's too much for today. You will die here. Or it's only okay.